Hello, everyone, to today's seminar on interval methods and control engineering. And it's my great pleasure to welcome Maria Luiza Costa Vianna today. And she received a double degree in electronics engineering from the Federal University of Rio de Janeiro and is in robotics from ENSTA Bretagne in Brest in 2019. And currently she's a PhD student, is co-supervised by colleagues from ENSTA Bretagne, Luc Jolin, and from two colleagues from the École Polytechnique à Paris, Eric Goubeau and Sylvie Puteau. And we're looking forward to your presentation, Maria, on a geometric approach to the coverage measure of the area explored by robots.
Okay, thank you, Andreas, for the introduction and for having me at the seminar. So I'm going to present a work in progress that was, of course, developed along with my thesis supervisors. And in this work, we solve a problem in robotics using topology and interval analysis. So I'm going to start this presentation with an introduction where I present the problem to you. Then I'm going to formalize the problem and present our topological approach to solve it. Then I'm going to present how we use interval analysis to implement the problem, and finally some results, and I will finish with a discussion around some possible leads for future work. Okay, so although our work can be applied and adapted to different systems and scenarios, you can see that we are interested in the problem of an autonomous underwater vehicle that explores an unknown environment. And this robot will have many sensors embedded. So I'm going to present some terms in robotics that are going to be useful for the rest of the presentation. And first we have navigation or proprioceptive sensors. They are sensors that are going to acquire information about the robot itself. So it's going to be measuring the robot's speed, acceleration, and so on. And then we will also have observation or exteroceptive sensors that, on the other hand, are sensors that are going to acquire information about the environment surrounding the robot. So we have cameras, sonars, lidars, and I left some other examples here. And you can see that our AUV will explore the environment using two side-scan sonars. And what are side-scan sonars? So side-scan sonars are sensors that are used to acquire an image, to create an image of the seabed that is under the robot. And the advantage of using sonars instead of cameras on the water is that the acoustic image will not depend neither on the light that is available and neither on the water turbidity. And here on the right, you can see an actual image that was acquired by two side-scan sonars. They were mounted on an AUV like in this configuration that you can see on the left. And you can see that in the middle, we have this black band that corresponds to the gap that we have between the two sensors from where we have no information. And then we can see the seabed with its textures on the right and on the left side of the robot. And these images, they are called waterfall images because as soon as new data arrives, we have the current image that shifts downward, so like a waterfall, like you could see at the animation. And in this work, to simplify, we are going to assume that the gap between the two sensors doesn't exist. So we added a gap filler. So this means that at any moment, the robot's visible area can be modeled as a line. So like we can see here, that it's projected onto the seafloor that is sensing a narrow portion of the environment. Okay. So let's now imagine a simple mission where the robot only moves forward. And during a mission, the area explored by the robot would be the union of the robot's visible area along its trajectory. So here in the example, the explored area would be this green rectangle that we have projected onto the seafloor. And our objective in this work is to estimate the explored area and also to estimate what we call the coverage measure of all the points in the plane. So the coverage measure is how many times a point in the plane was sensed by the robot during exploration. And we want to do this using only the information that comes from the proprioceptive sensors. Okay, so now I will explain why we want to do this. So to compute the explored area, the main application is to assess area covering missions. An area covering mission is a mission where the robot is required to cover with its sensors or with its tools a whole area of interest. So if you have autonomous vacuum cleaners in your home, you probably already saw this. But in the underwater environment, we are using these missions to do hydrographic surveys, to do in the search of wrecks and lost objects, and also in the search of potential threats. So for example, in the search of underwater mines. And if we can determine the explored area, we can determine if these missions are complete or plan other missions to fill possible gaps. And then for the coverage measure, so how many times a point in the space was explored by the robot. So a simple application is to plan optimized trajectories if we don't want the robot to cover the same area twice, for example. And for the two other applications, I'm going to use some images to explain. So first, I'm saying that the coverage measure can help in localization in homogeneous environments. So I'm going to explain very quickly how an algorithm of localization can work in robotics. Of course, there are many of them. I'm just going to explain one. So first, we do what is called a proprioceptive estimation. So here we take the information that comes from the proprioceptive sensors, and we are going to integrate them. So we are going to integrate the robot's speed, acceleration, angular velocities, and so on. And this will give us a first estimation of the robot's position. So here in this picture, you can see in black this trajectory. That is the robot's actual trajectory that we don't know, that we are trying to estimate. And then we have this blue envelope surrounding it. That is what we obtain from the proprioceptive estimation. And you can see that at the beginning, the estimation might be very precise, but as we propagate error through integration, it becomes less accurate. So here what we do usually is an exteroceptive update. So we are going to take now information that comes from the environment, and we are going to try to do a feature matching. So the feature matching process tries to determine that we are in a place that we've been previously by recognizing features. And if we can do this, we can refine our estimation around this point. And this technique is called loop closure, and it works very well in environments with a lot of features. However, if the environment is homogeneous, like the underwater environment, it won't be the same. So you can understand I have here 5 pictures that were acquired by side scan sonar, and they are pictures of 5 different rocks. So the majority of the algorithms of feature matching that we have today would probably say that they are the same, leading to a bad exteroceptive update. However, if we know that 2 of these pictures were taken around an area that we know that has a coverage measure of 2, for example, so an area that was explored twice, we could use this as confirmation that we actually had a loop closure here. Okay, and for the other application is to assess what I call revisiting missions. So this is a problem that was posed by the DGA, so the French Defense Agency, to the ROBEX team at ENSTA Bretagne. Because, so to understand, you can look at this image, another image that was acquired by 2 side scan sonars. And you can see that we have some rocks detected, some debris, and an underwater mine. So as you can see, sonar imagery is very hard. And to classify a mine as a mine and not as a rock, for example, you need to be an expert. So when they are doing area covering missions, looking for potential threats, They don't want what we call mine-like objects to be covered only once, but many times to help in the classification process. So to assess these missions, it's also important to know the coverage measure. Okay, so I'm going to formalize the problem that I just presented. So in this presentation, we are going to assume, at least for the moment, that the robot's trajectory is known. So we are not going to deal here with the uncertainty in the robot's trajectory. I will talk a little bit more about this at the end of the presentation. But for the moment, the robot's trajectory, it's a continuous curve in the plane that is known and that we call X. I'm also going to define the robot's visible area. So as I mentioned, it can be modeled as a straight line and also for the moment of fixed size that will only depend on the robot's position and orientation. Okay, and then the explored area, that would be the union of these visible areas over the whole trajectory. So to summarize, we have the robot's trajectory, we have the range of visibility of the exteroceptive sensors, and we want to estimate the explored area and the coverage measure of all the points in the plane. And we can, of course, define the explored area as a set of points whose coverage measure is bigger than 0, because these are points that were seen by the robot at least once. Okay, and how do we approach this problem? So from the knowledge of the robot's trajectory X and from the knowledge of the range of visibility of the sensors, we define the sonar's contour. So the sonar's contour is here represented in red, and it's an oriented closed curve, continuous closed curve in the plane. And the fact that the sonar's contour is a closed curve in the plane, it allows us to explore some interesting topological properties. And one of them is the property of winding number that we are going to be using. And the winding number, in a nutshell, it's an integer that represents how many times a closed curve in the plane surrounds a point in the plane in a counterclockwise manner. So here I have some examples. So first you can look at this region here in light gray. So all the points inside this area, they have a winding number of +1 because they are surrounded once by this cycle that is a counterclockwise cycle. And the points in the striped area, on the other hand, will have a winding number of -1 because they are surrounded once too, but in a clockwise manner. So it's only a convention. And then for the 8th figure, we will have the same thing. And here in this example, we have these darker gray areas that will have a winding number of +2 because they are surrounded twice in a counterclockwise manner. So the winding number we will be representing in this presentation by eta of a closed curve gamma, that for us will be the sonar's contour that I just presented, with respect to a point, and this value is an integer. Okay, and in this work, we are going to establish a relation between the coverage measure of a point in the plane and the winding number of the sonar's contour with respect to this point. And under some conditions that I'm going to discuss in this next slide with you, we are going to prove that these values are the same. And in this case, that we can define the explored area as a set of points such that the winding number of the sonar's contour with respect to these points is bigger than 0. So first we can see this visually here in the picture. So the points in the light gray areas, they have a winding number of +1, and they are also the points that were explored once by the robot. And they have a winding number of +1 because they are surrounded once by gamma. So you can see here that all these points, they are surrounded once by this counterclockwise cycle here that I just showed. And then we have these points here in white that were not explored and they have a winding number of 0 because they are surrounded once in a counterclockwise manner and then surrounded another time, but in a clockwise manner. So the winding number is +1 - 1, giving 0. And then we have these points here in the darker gray area. They are surrounded another time by this other cycle, leading to a winding number of +2. And that's why we have a winding number of +2, and these are also the points that were explored twice. So now I'm going to discuss very fast the proof of this affirmation, only so you can have an idea from where I'm coming from. And for this, I have to introduce two new terms that come from sonar terminology. They are the waterfall and the mosaic spaces. So the waterfall space that we represent here by W represents the road in the robot's point of view. So basically here in the abscissa, we have the lateral distance of a point to the robot, and on the ordinates, we will have the time of exploration of this point. Then we have the mosaic space represented by M, that is the world as we know. So it's where the robot's trajectory, the sonar's contour, and the explored area are defined. And we have this mapping function F from the waterfall to the mosaic space. So we can understand better, we are going to take a point P in the mosaic space. And the number of times that this point was explored by the robot is equal to the number of times that this point appears in the waterfall space, or equivalently, the number of times that this point P will appear in the waterfall image that I presented at the beginning of the presentation. So if we take the inverse of F here at P, we must have 2 points in the waterfall space. And the first time that the robot sees P is at the beginning of exploration and closer to the sonar left border. So that's why we will have something like P1. And then the next time that the robot sees P is towards the end of the exploration, and this time closer to the sonar's right border. So that's why we will have something like P2 in the waterfall space. So we are going to be using this relation in our proof. So first I'm going to define a new function, that's the function FP. That is basically the mapping function F shifted by a point P in the mosaic space. And I'm doing this because I want P to become 0 in this new function. So like I mentioned, the number of times that P was explored is equal to the number of times that P appears in the waterfall space. So the coverage measure of P is equal to the cardinality of the kernel of the inverse of FP. So the kernel of the inverse of FP is a set of points in the waterfall space that are mapped into P by F, and they are mapped into 0 by FP. So we have a set of points here in the waterfall space. So if you have K points, well, the cardinality will be equal to K. And in this previous example, K was equal to 2. And I'm not going into a lot of details here. Like I mentioned, it's only so we can have an idea. But by definition, we know that the topological degree of a continuous mapping function, that for us is FP, from a bounded region, that for us is the waterfall space, will be equal to the sum. So the sum is the sum of the sign function of the determinant of the Jacobian matrix of FP over the points of the set of the kernel of the inverse of FP. So that's why we are doing a sum over K. And if we assume that FP preserves orientation, this means that the sign function will always be +1. The sign function will be -1 if FP reverses orientation. So if we assume that FP always preserves orientation, we are doing a sum of +1s, and the topological degree would be equal to K, that is also equal to the coverage measure. So we are going to have something like this. And also by definition, we know that in the plane, this topological degree would be equal to the winding number of FP over the boundary of W with respect to 0. And from the definition of FP, we can rearrange things so we can have the winding number of the function F over the boundary of W with respect to P. That is equal to K, that is equal to the coverage measure. And we know that F over the boundary of W is actually the sonar's contour. So that's how we prove what we wanted in the previous slide. So I know that maybe it was too fast for a proof. So if someone wants to discuss it afterwards, I will be happy to do it. Okay, so like I mentioned, we are assuming in this proof that F will always preserves orientation. So this means that if F preserves orientation, the sonar is always sweeping forward. So here, if we look at this image, we have in black points that were not explored by the robot. We have these dark gray boxes that are surrounding the sonar's contour. And we have these lighter gray boxes that contain points that were sensed by the robot once, and they have a winding number of +1. So the robot started here, and then it moved forward, sweeping all the points in these light gray boxes once. And so here the sensor is only sweeping forward. And what happens if at some point the mapping function F doesn't preserve orientation, and therefore if the sonar's contour sweeps backwards? So we would have something like this happening. So we have here this edge and all these points that were swept backwards by the robot. And at this moment, the coverage measure will no longer be equal to the winding number value. Because if you look at the sum that I presented previously, we are going to be, the sum here will be doing a sum of +1 and -1, because +1 for the moment that we sweep forward and -1 for the moment that we sweep backwards. And in this case, resulting in a topological degree that is equal to 0, and therefore in a winding number that is equal to 0, that is no longer the value of the coverage measure. Because here we know that we have points that were swept twice by the robot, so they must have a coverage measure that is equal to 2, but the winding number will be equal to 0. So in this work, in this presentation, we are going to assume that this won't happen. So the sonar is always sweeping forward, and so F is always preserving orientation. And of course, this can happen in a real case scenario. So this is something that we might be addressing in some future work. Okay, so rearranging the problem, we have the sonar's contour. We want to estimate the explored area and the coverage measure of all the points in the plane. And we are going to do this by calculating the winding number of the sonar's contour with respect to all the points in the plane. And of course, we are going to do this efficiently using interval analysis. Okay. So like I mentioned, we have some hypotheses on gamma, of course, so everything will work. I just mentioned one of them. And I'm going to talk about 3 others that are going to be important so we can understand the rest of the presentation. And the first is, like I already mentioned, gamma must be continuous. Gamma must have a finite number of crossing points. So crossing points are the self-intersections of gamma. And gamma only passes through each crossing point twice. So here in this example, we have all these hypotheses that match. And we are going to start our algorithm by constructing a CW complex from the cycle gamma. So if you don't know what a CW complex is, it doesn't matter. What you need to understand is that I'm going to be decomposing gamma. So first, I'm going to detect the self-intersections of gamma. So here we have 4. Like I mentioned, we will only have a finite number of them. So here we have V1, V2, V3, and V4. And now we are going to decompose gamma in terms of edges. So the edges of gamma are connected components of gamma without its self-intersections. So if we remove the self-intersection of gamma, its edges are what we have left, are the connected components we have left. So we have 8 edges here in this example. And then we are going to detect the regions in which gamma divides the R2 plane, because gamma will divide the plane into a finite number of regions. So we will have a finite number of bounded regions that we can see here from A1 to A5. And we have an unbounded region that is the exterior. And so the regions are connected components of the plane if we remove gamma. And each one of these regions will have a winding number value. And that's what we are going to do now. We are going to attribute a winding number value to each one of the regions. And we are going to do this quickly and efficiently using two rules that I'm going to present right now that allow us to determine the winding number in all of the regions by knowing the winding number in only one of them. So the first rule is the Mobius combinatorial rule for defining the winding number. So here Mobius states that if we have two regions that share a boundary, their winding number values must differ, of 1. And by convention, since we are counting counterclockwise cycles, the region on the left must have the bigger winding number value. So for example, if we have this region here that has a winding number value of P, so P here is an integer, and we can see that consider the orientation of this edge, P is on the left. So the region on the right must have a winding number of P minus 1 according to Mobius. And then we can propagate this value again. So again, this region here is on the right, considering the orientation of the next edge. So we propagate this doing +1, and the next region must have a winding number of P. And how does this work in our problem? So we can start, for example, from the exterior, because the exterior is the only winding number, is the only region with a winding number that we know for sure at the beginning, that must be 0. So we start with 0 on the exterior, and then we can find all the regions that share a boundary with the exterior. So we have A1, A3, and A5. If we take the orientation of the edges that they are sharing, we can see that they are all on the left. So according to Mobius, we take 0 and we do +1 to obtain their winding number. And then we need to propagate this to the interior regions. They are A2 and A4. So starting with A4 that shares a boundary with A3. A4 is on the right, so we do 1 minus 1, and we obtain the winding number of 0. And now for A2, we can choose any one of these 4 boundaries that we have. I'm going to choose this one with A3. And A2 is on the left, so we do 1 + 1, and we obtain 2. So this is how, using Mobius, we can determine the winding number of all of the regions. And now I'm going to present an algorithm that is the Alexander numbering algorithm that is going to be using Mobius, but instead of Mobius, it will allow us to determine the winding number in all of the regions only by analyzing what happens at the self-intersection. So instead of analyzing all the edges. And considering the hypothesis that we established for gamma, we know that each self-intersection will be characterized by 2 lines that cross each other at some point. And they will be dividing the plane into 4 regions that we can see here. So according to Alexander, we can choose any one of these lines. It doesn't matter. So I'm going to choose the solid line here. And you can see that this line is divided into 2 edges by the self-intersection. So we start by numbering the regions that are surrounding this first edge using Mobius. So here on the left, if I have P + 1 as a winding number, on the right, I must have P. And according to Alexander, I can now propagate these winding number values to the next regions, considering the next line. So I know that this dashed line, that is the other line that characterizes the self-intersection, is coming from the right. So in this case, we can propagate these 2 values doing -1. So P + 1 becomes P, and P becomes P minus 1. Okay, so now another example. I'm still taking the solid line first. I'm going to number these 2 regions here, according to Mobius. So if I have P on the left, I must have P minus 1 on the right. And now the dashed line is coming from my left. So I propagate during +1. So P minus 1 becomes P and P becomes P plus 1. And it's the same principle of the Mobius rule. The idea is that we can do this because, again, we are counting counterclockwise cycles. So it's from convention. So we are going to use this in our algorithm. So first we detect the self-intersections that are represented here in red. And then we are going to use the Alexander algorithm to number all the regions. So we can start from any self-intersection that we want. I'm going to start from V1. We need to choose one of the two lines to start. I'm going to choose this one. So I number the regions surrounding the first edge, like Mobius. And then I see that the next line is coming from my left, so I can propagate to the next regions doing +1. So P becomes P plus 1 and P minus 1 becomes P. I can then move to the next self-intersection, V2. So the first edge is already numbered, so I can now take this next line that is now coming from my right. I'm going to propagate P as P minus 1, so it's already done, and P plus 1 as P. I will do the same to the self-intersection V3. So it's coming from my right, I propagate as P minus 1. So I don't need to analyze V4 because it would be redundant since I already have all my regions numbered and this numbering is unique. So now we numbered all the regions with a winding number in terms of a variable P. But we know that the exterior region must have a winding number of 0. So in this example, P must be 1. And this is how we number all of our regions with a winding number value. Sorry. Okay, so now that we numbered all the regions, we are going to create some sets using these regions. So I call the sets SI, and a set SI is the closure of the union of the regions with a winding value greater or equal to I. So in the previous example, we would have two sets. First, the set S1 with all the points that were explored at least once. And then we have this other set S2 with all the points that were explored at least twice. So we have these two sets for the previous example. And we are going to be using a theorem that allows us to compute the winding number for a closed curve using the sets. So doing a sum of the characteristic function of the sets. And for the previous example, we will have that the winding number is equal to the characteristic function of S1 plus the characteristic function of S2. So S2 and S1, they are represented here. And the characteristic function of a set at a point P is 0 if P doesn't belong to Si, the set Si, and 1 if P belongs to the set Si. So here, if we take P here in this example, it belongs to the two sets, so it has a winding number of plus 2. Here, P only belongs to S1, so it has a winding number of 1. And what happens if P is on the boundary of a set? So in this case, in the literature, the winding number is considered to be undefined. However, in our example, a point that is on the sonar's contour is a point that was explored by the robot at least once. So in our case, this point, the winding number for this point will be defined. And in this example here, it will be equal to 1. And like I mentioned, we want to characterize the explored area efficiently. So we are not going to compute the winding number for all the points individually. So we are going to compute the winding number for boxes instead of points. So the only thing that changes is that we had to adapt the characteristic function. So the characteristic function for a box is equal to the singleton zero if this box doesn't intersect the set, is equal to the singleton 1 if this box is a subset of the set, and in the interval 0, 1 otherwise. So for this example, the winding number would be equal to the singleton 1. And for this example would be the interval 0, 1. So the winding number contains all the possible solutions for the winding number that we have inside this box. And as I will mention in the results, you will see that the fact that we compute the winding number for boxes instead of points is that it will help to adapt our code to deal with the uncertainty in the robot's trajectory later. Okay, so some results. So for the simulation, I'm going to be using the codec library. So in red, you can see the robot's trajectory, and in blue, the sonar's contour. And this is the characterization that we obtain for the explored area. So here I'm using a CVA algorithm, so set inversion through interval analysis algorithm to characterize the explored area. So we have in green boxes that contain points that were certainly explored once, boxes in blue that contain points that were certainly explored twice, and in black, boxes that are uncertain. So when I say uncertain, it only means that the winding number value is not a singleton because it's on the border of the sonar's contour. And like I mentioned, we can also characterize the winding number for these uncertain boxes. So we have in gray points that were maybe explored once and maybe not explored. In pink, points that were explored at least once, but maybe 2 times. And in red, points that maybe were not explored, maybe were explored once, and maybe were explored twice. Sorry. So we also applied our algorithm to a real data set that was acquired by the robot Daurade that you can see here in this picture. So Daurade explores the environment using 2 side-scan sonars, like I showed at the beginning of the presentation. And of course, it also has different proprioceptive sensors embedded. So we are going to be using here a Doppler velocity logger that is used to estimate the robot's speed underwater. We also have an inertial measurement unit that will measure the robot's acceleration and angular velocities. And we have a pressure sensor that will measure the robot's depth underwater. And why do we need this? Because to the moment I was saying that the range of visibility of the sonars was fixed. However, this won't be the case in a real application because the sonar's range of visibility will vary according to the robot's altitude. So if you have its depth and the bathymetry of the place where we are, we can estimate the robot's altitude. So we acquired data from a small mission of almost 50 minutes that happened in the roadstead of Brest, and it was a classical survey path. So that's a classical survey path. So again, this is only the integration of the proprioceptive data, and I'm not considering here the uncertainty in the robot's trajectory. And then we have the sonar's contour. So you can see that the robot's altitude was almost constant. It varied a little bit around here, but not too much. And then we obtain the explored area. So in light gray, you can see points that were explored once. In dark gray, points that were explored twice. And in pink, points that were explored 3 times. And now only so I can give you a glimpse of what we will be doing in some future work, I'm going to show you what would be like if we consider the uncertainty in the robot's trajectory. So in this case, you can see that the robot's trajectory will get thicker with time because the estimation becomes less accurate. And the same thing will, of course, happen for the sonar's contour. So what will happen is, so I'm sorry for not using the same code color, but in green, we have points that were explored once, in blue, points that were explored twice, and in gray, points that were explored 3 times. And then in black, we have points that are uncertain. And as you can see is that what happened if we take into account the uncertainty is that points that are uncertain will become more common with time. And these boxes will become bigger. And we can also determine and characterize the explored area in terms of area that was certainly explored and area that was maybe explored, that we will be calling penumbra from the article of Benoit Desrochers and Luc Choron. And the idea here is that the penumbra gets bigger. So the penumbra is the points that we are not sure that we explored. It gets bigger with time as the area certainly explored reduces. So at some point, we will have only penumbra and no longer area that was certainly explored. So at this moment, we are going to need to use exteroceptive data that comes from the sonar in order to reduce the error in the estimation of the robot's position, and therefore to reduce the penumbra and to increase the certainty that we have in the area that was explored. So again, this is something that we are going to be doing in some future work. It's only so you could have an idea. Okay, so for conclusion, I'm actually going to talk about some leads that we have for future work. So we have, of course, a lot of them. I'm not sure I'm going to be able to do all of them with the time that I have left for my thesis. But so the first one is that there are very interesting works that relate robotics and topology, and especially using the uncertainty in the winding number. So we would like to study how our work can relate to these other works. And also there is an interesting article about covering areas using multiple robots and also related to topology. And that is something that we would like to do during the coverage area using multiple robots. And we think that our method can be easily adapted to do this, because since we are using a set membership approach, if we have multiple robots, we will only increase the number of sets that we have. So it should probably be an easy application. And then, of course, we are going to deal with uncertainty in the robot's trajectory, like I mentioned, and we will probably be using tick sets for this. So we are going to replace the sets as I's that I showed by tick sets. And then, of course, I would like to treat the problem where the sonar sweeps backwards. We are thinking about also some real-time computation. And finally, of course, a final application would be to use this to the localization when we include the exteroceptive data. So I think that's all I have to say. Thank you very much for your attention. And thank you again, Andreas, for the invitation.
Okay, and also many thanks, Maria, for a very interesting presentation. And now the floor is open for discussions. Who wants to start with the very first question? Okay, I think that's just a round of applause from Eric. Or Eric, do you have a question?
No, yes, that's just a round.
Maybe that's a little bit unfair if you would be asking the very first one.
Yes, Maria, I didn't understand this and that. Thanks,
okay. Now, is there anyone who wants to ask a question?
I think we have a question at the chat.
In the chat?
Slide 21. Yes, I'm going there.
Okay, this was sent privately to you.
Oh, it was sent privately? Okay. Yeah, it's very slow, my chat. I'm getting there. Yeah, so what is the... it's not a question, it's an observation. Okay, yes, it should be T minus. Thank you. It's not T plus and T plus.
Okay, a small typo that can be corrected before uploading the slides.
Yeah.
Okay.
Thank you.
Great. Do we have any question? maybe not a question, I just have a comment, because I think since I see here Marza, one of the PhD students here in Oldenburg, who is present in the audience, and I think it would be a very nice idea also to have a joint discussion with Marza concerning the use of thick sets in the case of multiple robots. I think this would be a really nice area in which we could possibly collaborate, because she's also thinking about doing some mapping and also localization using multiple mobile robots, not in an underwater environment, but in an indoor production environment.
Yeah, of course, for sure that is something that interests us.
Okay, then if I do not see any question, I have one. The question that I have, did you think about using your algorithm also for some kind of optimal trajectory or path planning?
Not yet. I think that's definitely one application that we could do, because before sending the robot to a mission, to an area covering mission, and especially if you want to do an area covering mission as quickly as possible, so not passing through the same place twice, I think that it could be an efficient way of planning these trajectories before doing the real mission. But we didn't apply it to this yet. But yes, in discussions, we thought that it could be one of the applications.
Yes, and I think also making a combination of such a, let's say, uncertainty prediction, where you're predicting how far the uncertainty of the robot position gets more imprecise from one point of time till the next, and combining this with your coverage measure, I think that's a really nice application also for an offline planning of some missions.
Yeah. Yeah, we will probably because for the moment we were more working in the theoretical part of the problem, but yeah, probably more towards the end of the thesis we are going to do more applications. So yeah, maybe if we have the time, that's something that we would like to do.
Okay, now I see that Luc wants to comment.
Yeah, no, it's a small question because so I think the approach you can make the fusion between different missions that has been done by the same robot at different time or by different robots, for instance. But when I see your slide number 6, for instance, maybe you can go to the slide number 6.
I'm going, it's very slow, but I'm getting there.
Yeah. Oops.
Okay.
I see that here you fill the gap between the left sonar and the right sonar. And I think it can be a problem, but probably what could be done if you can make the fusion is you can consider the same mission as 2 different missions, one done with the left sonar and one with the right sonar, and make the fusion between the 2 different left and right missions, no?
Yeah, I think we could do this too. Especially like I mentioned, since we are using a set membership approach, so we are dealing with multiple sets, I think we could effectively divide the mission into 2 different parts, as if we had 2 different robots, and yeah, it could work, I think.
Okay, good. Thank you. So congratulations for the nice talk.
Thank you.
Clear.
Okay, now let's see, do we have any further questions? I think this isn't the case at the moment. Then again, many thanks, Maria, for your interesting presentation. And
thank you.
Yes, I think definitely at least some of us will continue the discussion in a few weeks in Hanover at the swim workshop.
With pleasure.
I'm just looking here at the list of participants, and I think lots of us will be there present. And yes, again, many thanks to all of you. Have a nice Friday afternoon, evening, and weekend. And we'll have still one final presentation in our seminar series before the summer break. And the last speaker on Friday in 2 weeks will be Katharina Auer from the University of Applied Sciences in Wismar. She will give the final presentation before the summer break. And yes, see all of you soon on Friday in 2 weeks.